over here. But we'll do another recap at the beginning of next week. But I think we have enough time to go to cover virtual memory. So why do we need a virtual memory, right? That's the first thing you need to ask. Because you want unlimited memory. And you want to have this virtual view of your own memory. When you write a program, right? Let's say you run 10 applications. You have Google Chrome, your Microsoft Teams. In the background, you have Dropbox open. You have Google Drive, right? And you have Windows, which also is a program. So it has to run multiple processes. And then you have a control panel that actually have printer service like opening up, right? In case you have a print job, right? When you write this program, it's a good idea to make sure that when you write a program, you don't have to consider what else are running at that time, right? So you want this virtual view of your own data, your own memory. This allows you to assume that, hey, whatever I do here is just mine, right? And no one else can touch it. The programmer should not have to worry about where each of the processes, the memory are, unless you are working with embedded processor, which sometimes it might not support the virtual memory that well. Right? Most of the time, you want to just control your application accesses, and that's all. You don't want to worry about the other program running on the machine. You also want to have memory protection. It means that let's say I have two applications running, right? And let's say they run in parallel. One application in CPU 1, the other application in CPU 2. One app should not be able to read or write the data into the other app's memory, right? User should not also be able to read or write to the kernel's data, right? You need memory protection. You need you need a way to ensure that your program is safe. How many of you run into this thing called segmentation fault? Anyone see that before? So if you write code in C, right, and you use pointer, one thing that can happen is the pointer store the address, right? And by some accident, let's say your program has a bug and the address point to some other program's data, virtual memory, the memory protection would kick in and say, hey, you're trying to access some illegal data. So you're not supposed to be able to go there. It will kill the program and throw you this segmentation fault. Basically, it means that, hey, you're trying to access some illegal data that you do not own, right? This is actually a good thing in a sense that you crash the program and you get a seg fault rather than by accident you modify someone else's data. That's the worst case scenario that should not ever happen, right? So what exactly is virtual memory? Basically, in virtual memory, what we would assume, right? What we assume is that each program will maintain its own address, right? And the address, which is managed by the OS, will have just a mapping where that, hey, this address maps to this location in DRAM. This address maps to this physical address. So virtual memory is when you have the virtual address, right? Virtual address, you have the map between virtual address to the physical address, PA. So that's your mapping. And each process will have its own view of the memory addresses. So DRAM, the location of your data in DRAM, that's the physical address. So this is a location, right, in DRAM. Virtual address is the address seen by the programmer. Sorry about my handwriting. So the programmer sees the virtual address and the location itself is in the physical address. And the system and hardware will manage the mapping between virtual to physical through this unit called the memory management unit. It manages the translation between virtual address to physical address. All right, again, the key here, your program, right? Your program, the virtual address, the MMU process this through the process called address translation. And you get the physical address, which is the location in DRAM. So if we can keep this abstraction, what it means is every single program can now access the location in DRAM. But then, because each program has its own virtual view of the memory, right? I can just use the address all I want, and then the OS, the operating system, Windows, Linux, Mac OS, with the capability of the CPU and the MMU, they would provide the mapping and would manage, hey, this address goes here, this address goes there, right? So that's automatic by the OS, the kernel, the kernel in the OS, and the ISA and the hardware. So the first benefit is each program has its own virtual space. That's how you can have unlimited memory, right? Technically, as I said earlier, this is limited. This is your hard drive, right? So if you have any rarely used data, you move that to hard drive. For frequently used data, you keep that in the main memory. And these day and age, actually, there's multiple papers that talk about how to actually manage these data. For example, me and my colleagues in Hong Kong just published, and we have been working in the topic of like, how do we keep the data from the user that the user want to use, right, in mobile phone? How to make sure that we keep the frequently used data inside the memory and make sure that we don't page things out, because the memory on the mobile phone is actually really small compared to your desktop, right? So these are still a topic of research. The second benefit is, well, virtual address can be mapped to a much bigger space outside of DRAM, which is a hard drive, right? This is done through the page table structure. It would tell the location of your data. Then one page is a range of address, typically 4 kilobytes. It can be much larger. We'll talk about this in the next lecture on what if we don't use 4 kilobyte page, right? It provides certain benefits. And this is actually a topic of my own research, how to make a huge page. Basically, we now maintain the page as a much bigger granularity, how to make it work. So here's the page table structure. Basically, page table structure is a structure that determines the physical address when I have the virtual address, right? I apply the concept indirection again. So we saw indirection in out of order already with those like reservation station, all those things, right? We can use the same concept again here. I will explain this step by step, right? The page table, as the name suggests, is a table. It's a table that looks like a tree structure. All of these tables are inside DRAM, inside the main memory. And if you look at your processor from Intel, and it's likely that M1 and M2 processor as well, you have 4 levels of the page table, where you have the root point to the first level. You then use the virtual address, basically the address you see in the program, along with the information from the page table structure to figure out where is my second level. From the second level, again, you use the virtual address to go to the third level, so on and so forth, right? So let me translate this quickly using analogy in Thai. น้องคนไหนเคยเล่นแบบพวกแบบการเกมหาขุมทรัพย์ไหมที่แบบตอนแรกเราจะมีคลูให้ก่อน1 อันแบบเป็นคลูให้ก่อน1 อันแล้วเราจะดูคำใบ้อันเนี้ยเพื่อไปที่คำใบ้อันที่2แล้วคำใบ้อันที่2มันจะบอกว่าคำใบ้อันที่3อยู่ตรงไหนแล้วคำใบ้อันที่3จะบอกคำใบ้อันที่4อยู่ตรงไหนอันนี้เคยนึกภาพออกไหมฮะนึกภาพออกไหม virtual address อ่ะก็คือสมมุติเรามี address ของเราอยู่ใช่ไหมเราจะใช้ information ที่เป็น address ของเราเนี่ยมาเป็นมาร่วมกับไอ้คำใบ้ก็คือเรามีคำใบ้บอกคำใบ้อาจจะบอกว่าเอาบิตนี้ของ virtual address ตรงนี้มันจะไปบอกว่าคำใบ้ที่2อยู่ตรงไหนแล้วพอเราไปที่คำใบ้ที่2คำใบ้ที่2ก็จะบอกว่าเอาบิตนี้ถึงบิตนี้ของ virtual address มารวมกับ table ตรงนี้ของคำใบ้ที่2เนี่ยที่มีอยู่ในกระดาษแผ่นเนี้ยมันจะบอกได้ว่าคำใบ้ที่3อยู่ตรงไหนคำใบ้ที่3ซึ่งมันก็เป็น table คือมันด้วยความที่มันเรียกว่า page table เนาะคือมันชื่อก็ตรงๆมันจะเป็นตารางอันหนึ่งแล้วมันจะบอกว่าใน virtual address มันจะบอกว่าตารางเนี้ยเราต้องไปดูที่ช่องไหนแล้วช่องนั้นมันจะบอกว่าคำใบ้ที่4อยู่ตรงไหนทำอย่างเงี้ยไปเรื่อยๆจนถึงสเต็ปสุดท้ายไอ้คำใบ้อันสุดท้ายมันจะบอกว่าเอาพาร์ทนี้ของ virtual address มาบวกกับพาร์ทนี้แล้วเราจะได้ physical address นะครับตัวอย่างมันจะแบบนี้เลยคือมันจริงๆมันก็เป็นเหมือนไอ้ table เนี่ยมันจะเป็นคำใบ้ที่ชี้ว่า table อันต่อไปอยู่ตรงไหนนะครับแล้วที่ผมบอกว่ามันรูปร่างหน้าตาเหมือน tree อ่ะเพราะว่าไอ้คำใบ้อันแรกอ่ะมันก็จะชี้ไปคำใบ้อันที่2คำใบ้อันที่2ก็จะชี้ไปสเต็ปต่อไปเลเวลที่เลเวลต่อไปเรื่อยๆจนครบ4เลเวลแล้วเราก็จะได้ physical address เนาะ so that's basically how translation works right each page table store the entry. So inside the table, because as the name suggests, it's a table. So you have rows of data, right? Each row, we call that the page table entry. The page table entry acts like a tag that provides the information on where the next table is located. The page walk process, if you read the textbook and it says page walk is I go through this table structure so that I can get the physical address. So here's one example. Let's assume we have two levels. These are the 32-bit machines. So back in the day, year 2000, right? Year 2000, your CPU is still using the 32-bit CPU. 32-bit CPU, x86 has two levels of the page table, where each table has 1000 entry. It's 32-bit for the address because it's a 32-bit machine. You have 1000 entries in the table, right? Each entry is four bytes. So in total, this is 4 kilobytes for the entire table. I can ask you this, right? Given this virtual address, what would be my physical address, right? But here, let's go through a more concrete example, right? Using Intel 32-bit x86 page walk, right? So over here, what I just showed, let's say this is my address. It's just a bit pattern, 01010101, whatever bit pattern they are. Because we have two levels, I can break these things into 3 different sections. The rightmost part, the lowest bits, these are what we call the page offset. The page offset would tell you the location of my data inside a page, right? Because a page is 4 kilobytes in size, your access, let's say it's an integer, right? Integer access is 4 bytes. So it tells you where is your data inside that 4 kilobyte page, right? So that's the page offset. How many bits do we need for the page offset? You need to be able to tell every single byte from this whole thing, right? This whole 4 kilobyte page, which means that you need log of 4 kilobytes. That's 12 bits. So the 32-bit x86 use the last 12 bits for the page offset. The other 20 bits, because you already used 12 bits, you have 32 bits in the beginning. 32 minus 12 gets 20. You can actually split them into 10 and 10. The first part, some textbook would call this page directory. Some textbook, or I will call this level 1 index bits. The second part is called the page table. Again, I call it level 2 because these days you have 4 levels. So it could go level 1, level 2, level 3, and level 4. The page table structure, right? This whole thing, including the status bit, this is called the page table entry, right? Page table entry. And this whole thing is called a page table. So let's say that this level 1 index bit is 0, 0, 0, 0, 0, 0, 0, 0, 1, 1. Those are 10 bits, right? What's the number there? Can someone tell me what's that number? Oh, zeros and ending with 1, 1. That's 3, right? That's 3. So let's say bit 31 to bit 22 is 0, 0, 0, 0, 0, 0, 0, 1, 1. What we do here is with that clue, we go check the page table by going to row 3, going to that row. The bits tell you what row you're going to. So in this case, you go to row number 3. Row number 3, you see something. The status bit will have the permission, right? Can I access these data? And then this part will tell you the location of the next table. So that part will be an address, of the next table. That's the second level table. So whatever is stored in here will be the address that you can use to go to the next table. Then let's say level 2 index bit is something like 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, right? So that's 4, right? So in this case, which row do I go to? Earlier on, the index bit is 3, so I go to row 3. Now it's 4, so I go to row number 4, right? Now it's go to row number 4. So that's, because this is the last level, what you can do to get the physical address is take this part, whatever bit is that. This will tell you the address of the page, right? So the page looks like this. This is your page. That's where your data is. It has some starting address, and it has the end address, the last address inside the page. And this is 4 kilobytes long, right? Then you use the page offset, right? So the page offset will tell you how far do you have to go in here to get your data, which is, say, right here, right? So to get that, you can then just take those bits, then you plug in the page offset and you're done. That's your physical address. This is basically this is your physical address. All right. Again, I'll give you some exercise that you can do, and we'll do that again next week at the beginning of the lecture. So we have the caching exercise and we have the translation exercise. All right. And the way the page walk in the 64-bit machine, which is your modern day CPU, works almost the same way. Again, it has a starting address. There'll be a register to tell you where is the first table. It's called CR3 register. The CR3 register in your CPU will tell you the address of the first level table. Then you use that index to go into that entry, which will tell you the next table. You use the index in the next level in your virtual address to go to the next table and then the next table again, right? Now, in the 64-bit machine, the level 2 PTE will have some metadata that tells you, okay, how often have I accessed these pages? Can I actually access them, right? And then you go to level 1, right? Level 1 will have the permission bits, which will keep track of who owns the page and whether it's a kernel or user, is it read only or read write, right? So these things would allow you to make sure like the OS can maintain those permission bits to make sure every single data access is legal, right? So it does come with performance overhead, right? We will talk about this next week in more detail, but now I want to motivate the problem. Because let's say you have 4 levels of the page table, right? To get your physical address, right? So you have virtual address in the beginning, you want physical address. This is location in DRAM, right? But your page table is in DRAM. So when you have data access and you have 4 levels of the page table, you cannot go to DRAM. You cannot go access your data until you know the physical address. But to get your physical address, how many trips to DRAM do you have to do already if you have 4 levels? If you have 4 levels, you have to go to DRAM 4 times to get the physical address before you can access your data. That's bad, right? The second problem, you have cache, right? In modern chip design, but you need the physical address for the tag. We will talk about why, and we will talk about how do we deal with this. But that's the second problem. You cannot even go to the cache unless you have the physical address. All right. So that's it for today's lecture. We'll continue on in the next lecture. As I said, I'll post some sample questions that you can try out. If you're busy, it's fine. We'll go through those questions in the beginning of the lecture next week. And that's it for today's lecture. Any questions? มีคำถามไหมครับ